Greetings, ladies and gentlemen. I welcome you all to TV Math Hub. Today we shall be exploring more of the basics of what we call the basis and dimensions of the subspace of a given vector space. I encourage all of us to subscribe to TV Math Hub for easy to follow math lessons. Just hit the subscription button and you will always get notified in case a new video will be uploaded. So let us get started. We are looking at one more example about the basis and dimension of the subspace. And now we shall consider the polynomials, that is the polynomial space, which is basically of degree 3. So let us look at this question. Find a basis and dimension of the subspace W of V, which is our vector space V, that is spanned by the polynomials. We have V1, V2, V3, and V4. Like the way we did in our previous example, which was about the basis and dimension of the subspace, we basically need to form a matrix, and after forming a matrix, we reduce the matrix to form an echelon matrix. After forming an echelon matrix, the non-zero rows will give us what we call the basis, and from the basis we shall be able to come up with the dimension. So we shall follow the same and look at the solution for this question. So the solution. Now, from the given polynomials V1, V2, V3, and V4, we shall be interested in getting the coordinate vectors. So we shall obtain the coordinate vector of each of these polynomials in relative to what we call the standard basis. So the standard basis for the polynomials of degree 3 will be t to power 3, t squared, t, and 1. So the coordinate vector of V1 relative to this basis here will be same as 1, negative 2, 4, and 1 by simply taking the coefficients for t to power 3, t squared, t, and the constant terms. So we shall be able to obtain this. Then the coordinate vector for V2, you simply take 2, negative 3, 9, and negative 1. That is with respect to the standard basis. So that is why we have this, and similarly we shall do for V3 and V4. So from that we shall be able to form the matrix whose rows are these given vectors. Then we shall now row reduce it until we obtain what we call the echelon form. As we said in our previous lecture, when you obtain the echelon form, then you have to look at the non-zero rows, and those non-zero rows will be forming what we call the basis, and from that you will be able to get the dimension. So let us look at the matrix corresponding to these vectors. The matrix corresponding to these vectors will be this matrix: 1, negative 2, 4, 1, 2, negative 3, 9, negative 1, and others. So that is the matrix corresponding to the vectors. So these are the coordinate vectors we are considering. We take the row form, so they will be treated in a row form. So from that we shall be able to obtain this matrix, which matrix we can now use the row operations until we obtain the echelon form. So looking at these operations, we shall be interested in creating a 0 here, creating a 0 here, and creating a 0 here. So we shall use these operations here. So from these operations, we shall be able to get this matrix. So we want to apply more operations until we get the echelon form. So let us create also 0 here and 0 here by using row 2. So using row 2, to create a 0 here, we shall apply -2 in row 2 plus row 3 to give us row 3. The effect should be here. And row 2 plus row 4 to give us row 4. We want the effect to be here. So when we do that, we shall be able to obtain this will remain the same, 1, -2, 4, and 1. And this one here will be 0, 1, 1, -3. It is still remaining the same. When we apply our operations, of course, this will remain 0. So this is -2 multiplied with 1 plus 2. It will also be 0. This is -2 plus 2. It will also be 0. This is +6. That is -2 times -3. +6 plus -6, that is 0. This will be 0. This will give us, we are adding this and this. This and this will be 0 as well. This and this will also be 0. This and this will also be 0. So we shall obtain such a matrix. So having got our echelon form, we can now deduce the basis and the dimension. So the non-zero rows, what are the non-zero rows? So the non-zero rows we have the non-zero rows being 1, -2, 4, and 1. Then we also have 0, 1, 1, and -3. So these are the non-zero rows. And of course, from that, we can easily see that our dimension will actually be what? Our dimension will actually be 2. So from here, we can give the conclusion that the non-zero rows, which we have seen, 1, -2, 4, and 1, 0, 1, 1, and -3 of the echelon matrix form a basis of the space generated by the coordinate vectors, and the corresponding polynomials, we can easily get the corresponding polynomials from here because you are dealing with 1, -2, 4, and 1. So it means the corresponding polynomial to this one is the coefficient for t cubed, because we know the standard basis is containing t cubed, t squared, t, and 1. So of course, the first value is the coefficient of t cubed. Then the second value, -2, is the coefficient of t squared. And the next value, which is 4, is the coefficient of t. And if this is 1, then it remains 1 times 1. So basically, the corresponding polynomial to this will be t cubed minus 2t squared plus 4t plus 1. And similarly, for this, it will be the corresponding polynomial will be t squared. Of course, this is 0, so it means the coefficient for t cubed is 0. Then plus t, then -3. So these two here will form the basis for the w. So the basis of w will be containing these polynomials. This will be the basis, and of course from there we can deduce that the dimension will be 2. So the dimension of w becomes 2. So that is how we can treat such numbers if they are involving polynomials or if they are just given as vectors. Let us now talk about ordered bases. So we shall let S to be a set which is containing vectors u1, u2 up to un. If this is a basis for a vector space V over a given field F, since V is a set, then it means there is no ordering of its elements, meaning that uh, if you consider S to be your set, you can write U1, U2, U3, you can begin with U5, any, so long as they are elements within this given set. However, if the order is taken into consideration, then what we obtain will now be a basis which is ordered. Now, let us look at the definition of ordered basis. The ordered basis for a vector space V of a given dimension n is a basis having elements U1, U2 up to Un together with a one-to-one correspondence between the set and the set of natural numbers from 1 up to n. In other words, when you are looking at the basis, but you are taking in consideration the position of the elements, then we shall be saying that that basis will be ordered. So you realize you have U1, U2 up to Un. In other words, if this is U1, then the next one must be U2. The next element after 2 must be U3. So in case there is U5, and then there is again any other value, maybe U8, then another value, maybe U6, then this one here becomes unordered. So it must be ordered in such a way that from U1 you go to U2, you go to another element, which is U3, which is from 3 you must go to 4, from 4 you must go to 5. So there must be that kind of correspondence between the set that is under consideration and the set of natural numbers from 1 to n. So if we have our n elements, then they must be ordered in such a way that they are in the positions, or the positions are arranged in such a way that they correspond to this given set. For example, when you talk about the standard basis for R3, then the standard basis for R3, we know when you are looking at standard basis for R to power n, then you are considering elements such as 1, 0, 0 up to the nth term, which is 0. You are considering the next one to be 0, 1, 0 up to the last term, which is also 0. So the trend continues up to when you reach on the last value, which is 0, 0, 0 up to the last value. Now it will be 1. So you can easily see how ones are positioned in R to power n. This is the standard basis for R to power n. So looking at how the ones are positioned, so you can easily realize you can start with 1, others are zeros, 0, then 1 in the second position. Here 1 is in the first position, the second position, meaning in the next it will be in third position. So up to the last value when it will be in the last position. So looking at such arrangement, if you are talking about R to power 3, so the standard basis, the U1 will be having 1, 0, 0, then U2, 0, 1, 0, U3, 0, 0, 1. So such an arrangement is what we call an ordered basis. So if they are arranged in this way, then we can say that this is an ordered basis. Let us now talk about the coordinate of a vector. We shall begin with the definition. So we shall be considering an ordered basis for a vector space V, and that ordered basis is B, which is consisting of vectors V1, V2 up to Vn. If we let an element V from the vector space V such that this V here can be expressed as a linear combination of the vectors V1, V2 up to Vn. In other words, we can write this V as a linear combination of V1 up to Vn as alpha 1 V1 plus alpha 2 V2 plus up to alpha n Vn. So where alpha 1, alpha 2 up to alpha n are scalars. So if we have this V, which can be written as a linear combination of these vectors v1, v2 up to vn, then it means we shall be in position to obtain these scalars here if v, v1, v2 up to vn are known vectors. So if we can be in position to obtain alpha 1, alpha 2 up to alpha n, then we shall be calling these as scalars alpha 1, alpha 2 up to alpha n as the coordinates of the vector v, the coordinates of v. This alpha 1, alpha 2 up to alpha n are the coordinates of this v in relation to the basis, which is v1, v2, v3 up to vn. So alpha 1, alpha 2, if you express v as a linear combination of v1, v2 up to vn, then you obtain your alphas, that is alpha 1, alpha 2 up to alpha n. Then we shall be calling alpha 1, alpha 2 up to alpha n as the coordinates of this v, then relative to the basis, which is containing v1, v2 up to vn. So this vector here that is consisting of the coordinates is what we call the coordinate vector of v relative to b, and we shall be denoting that by v relative to b. This is the basis b, this is the vector under consideration, and it will be consisting of alpha 1, alpha 2 to alpha n. This it will be consisting of the scalars. So in case you need the coordinate matrix, this is one way of representing it, that is when you are using commas. Then in case you need to write the coordinate matrix of v relative to b, then the coordinate matrix we shall be denoting it using the square brackets, but we shall be using what we call a column matrix to represent the n tuple of r to power n. So in other words, you can write it in this form here, or you can write it in this form using commas. When you don't use commas, then you can write it in the coordinate matrix form. So those are the two different ways of how we can represent the coordinate vector, either using what we call the commas, or you eliminate the commas and use the column matrix. So we shall look at the examples, but this is more similar to what exactly we have been doing, because we know how to express a vector as a linear combination of other vectors. But in this case, we shall be considering the vectors in what we call an ordered basis. So let us look at some examples. Let us look at example number 1. We need to find the coordinate vector of this v, which is from R3, that is relative to this basis. So looking at that, we are given v, so we need to get v, the coordinate vector of v relative to the basis, and the basis that we are considering for this case is actually an ordered basis. It is not ordered basis. So for this case, we are considering v with respect to the unordered basis, which is f. So we need the coordinate vector of this. As we have seen, we need to first of all set v as a linear combination of these f's. So we shall say we shall set v as a linear combination. We set v as a linear combination of the fi's, in other words, of f1, f2, and f3. We set this as a linear combination of the fi's, that is f1, f2, and f3, using some scalars. Using scalars, we can have our scalars as alpha 1, alpha 2, and alpha 3. So we must maintain the order that is given here. So for that case, we shall have v as alpha 1 f1 plus alpha 2 f of 2 plus alpha 3 f of 3. So we are making v as a linear combination of f1, f2, and f3. Clearly, v is given, f1 is known, f2 is known, and f3 is known. So what we shall do is to simply substitute for v, f1, f2, and f3. So when we do that, we shall be able to get this expression. So substituting for f1, f2, and f3. So this is our v, which is given here. So using the column form, we can easily place this one in column form, so as we can easily manipulate this expression. So from here, and trying to simplify this expression, we should be able to obtain this. That is alpha 1 times 1 plus alpha 2 times 0 plus alpha 3 times 0. So here we are adding the corresponding components. So we shall be able to get this column vector or the column matrix, and we equate it to this. So equating these two here, if the two must be equal, then the corresponding components must as well be equal. So for that case, we shall equate alpha 1 to 3, alpha 1 plus alpha 2 to 1, and alpha 1 plus alpha 2 plus alpha 3 to negative 4. So doing so, we shall be able to obtain these equations here. So let us try to manipulate these equations. So far we have already got alpha 1. So it means from equation 2, from 2 we shall have 3 plus alpha 2 equaling to 1. And for that case, alpha 2 will be 1 minus 3, and this is negative 2. Also from equation number 3, we have alpha 1 already as 3. We have alpha 2 as minus 2, then plus alpha 3 equaling to negative 4. So this will give us 1 plus alpha 3 is equal to negative 4, and this will give us alpha 3 as negative 5. So we shall be in position to get alpha 1, alpha 2, and alpha 3. As we said, v can now be written thus. It means our v can be written as alpha 1, we have got it, alpha 2 we have, and alpha 3 we have got that. So v can be written as actually a linear combination of, that is alpha 1 f1 plus alpha 2 f2 plus alpha 3 f3. That is what we had. So we have so far already got, this is the expression, we have so far already got alpha 1, alpha 2, and alpha 3, meaning v can be written as alpha 1, which is 3, f1, alpha 2 is minus 2, so we shall have f2 there, then alpha 3 is negative 5, f3. So if we want the coordinate vector, of v relative to the basis f, which f was containing f1, f2, and f3, we shall simply be taking these components here. So these are the components that will make a coordinate vector, and these components are the scalars that we have found: alpha 1, alpha 2, and alpha 3. So in other words, the coordinate vector, therefore the coordinate vector of v relative to the basis, our basis was f. So v relative to f, this is the vector v relative to f, will have the coordinate, which coordinate is 3, negative 2, and negative 5. That is the alpha 1, alpha 2, and alpha 3. So after getting the scalars, then they will be able to give you what we call the coordinate vector of v relative to the basis f. Now let us look at the case where the question is set in the other way around. So in our previous example, we were talking about getting the coordinate vector, which is v relative to what? Relative to the basis f. But now, suppose you are given this v relative to this basis f containing vectors f1, f2, and f3, and we are required to get the vector v. So you are required to get this v when you are given the coordinate vector and you are given this same basis. We are considering the same basis. Now, how do we get that? So we can easily get that because we understand that to get the coordinate vector of v relative to the basis f, then you consider the scalars, which scalars can be alpha 1, alpha 2, and alpha 3, such that this v can be written as a linear combination of this f. So when you are looking at v, it implies that if you are having this, then it implies that v can be written as a linear combination of the vectors in f. And for that case, in f we had f1, we had f2, and we had f3, meaning that these ones here are the scalars. So in other words, this is 3, f1, this is minus 2, and this is minus 5. So these are the scalars that form the coordinate vector of v relative to this f. So in other words, when you are given the coordinate vector of v relative to this basis, then it means v can be written as a linear combination of the vectors in this basis using these scalars in their order. So we were given our f, which was containing f1, f2, and f3. So we are using the same basis to answer this question here. So to get the vector v, then we have to write this v as a linear combination of the f or the vectors in f using these scalars here. Like the same way we had v written as a linear combination, that is alpha 1 f1 plus alpha 2 f2 plus alpha 3 f3. So for your case now, your alpha 1 is 3, your alpha 2 is negative 2, your alpha 3 is negative 5. So v can be written as 3 f1 minus 2 f2 minus 5 f3. So we need to get v. So we shall have v equaling to 3 into f1. So we had our f1, which is 1 1 1. So we shall have this as f1, this is 1 1 1, then plus this is negative 2 into 0 1 1. Again, this is negative 5 into 0 0 1. So that is what we are having so far. So looking at this, we simplify this. So this will be 3, 3, this will be 3, this will be plus, this will be 0, negative 2, negative 2, this will be again plus 0, 0, then negative 5. So basically we add the corresponding components, and this will be 3 plus 0, so it will remain 3. This will be 3 plus negative 2 plus 0, this will be 1, and this will be 3 minus 2, 3 minus 2, that is 1. So we have 3 minus 2 minus 5, so this is minus 7, and this will give us minus 4. So we shall be in position to get v, which is a vector from R3, whose coordinates, it means the coordinates for this vector here relative to the basis f will be this one here, because we can easily see that this v can be written as a linear combination of the f's, which is f1, f2, and f3. So this will be our v. So clearly you can easily see the same v we have here is actually the v we shall obtain when the question is set in the other way around. So you can easily get V when you are given the coordinate vector relative to this basis, and you can also get the coordinate vector when you are given V relative to the basis. Let us look at another example. In our next example, we shall talk about the matrix space. So we need to find the coordinate vector of A, which is relative to the standard basis for M22. So we need to know what is the standard basis of M22 before we get the coordinate vector. So looking at that, the standard basis of M22, the standard basis of M22 is, so this will be, we can call it B. So B contains matrices of this nature. 1, the standard basis, you begin with 0, or you begin with 1, 0, 0, 0. This is the first matrix. It should be of the order given A, B, C, and D. But the first element will be 1 when others are zeros, because we are talking about a 2 by 2 space. So it should be of this form. So this is 1, 0, 0, 0. Then the next one will be 0, 1, 0, 0. The next one will be 0, 0, 1, 0. The next one will be 0, 0, 0, 1. So this is the standard basis of M22. And as we said, the dimension of this is same as 2 times 2, which is 4. So clearly there should be 4 vectors in the standard basis of B. So which vectors must be of this form? So if it is of this form, then we shall say that this is a standard basis. So clearly we shall have a standard basis of this nature. So in case some other values change in this basis here, so it will no longer be a standard basis. However, it can also be a basis of M22 if it satisfies the condition for the what? The conditions for the basis. So we have our standard basis as this. Then we are having our vector. We are having a vector which is 1, negative 2, 3, 2. So the given vector is A. So we need to obtain the coordinate vector. We need to obtain the coordinate vector of A relative to the standard basis, which is B. So we need this one here. So to obtain this, as we said, we must write A as a linear combination of vectors in B. So that is how we shall be in position to get that. And for that case, we must seek some scalars such that we can write this matrix here as a linear combination of these matrices. So we shall, of course, set A as a linear combination of these matrices using the scalars. For example, there are 4 of them. So using the scalars alpha 1, alpha 2, alpha 3, and alpha 4. So set A as a linear combination of the matrices in the basis B. So for that case, we shall be able to get A as a linear combination of these. So we can write it at once. That will give us A, which A is 1, negative 2, 3, and 2, which is equal to alpha 1 into 1, 0, 0, 1, plus alpha 2. We are making A as a linear combination of these matrices in the standard basis. So that is alpha 2 into 0, 1, 0, 0, then we shall have plus alpha 3 into 0, 0, 1, 0, then plus alpha 4 into 0, 0, 0, 1. So we shall have that. So from here we shall now try to compute what we have on this side, because we can easily see this is a 0 here. So we can easily see that alpha 1 will be multiplying here, alpha 2 will be multiplying with this, alpha 3 with this one, alpha 4 with this, because all others are zeros. So in the next case, we shall have 1, negative 2, 3, and 2, which is equal to, so when we try to compute this one here, you realize you will have alpha 1, alpha 2 here, alpha 3 here, alpha 4 here. So this will give us alpha 1, alpha 2, alpha 3, and alpha 4 when you add the corresponding entries. So for the two matrices to be equal, of course, alpha 1 must be equal to 1, alpha 2 must be equal to negative 2, alpha 3 must be equal to 3, and alpha 4 must be equal to 2. So from there, we need the coordinate vector of A relative to the basis B. And for that case, you look at how A is written as a linear combination of the matrices in B. So we write that one using these colors here. We do that using these colors. So your A, the coordinate vector of A relative to B will simply become your scalars, which is alpha 1, alpha 2, alpha 3, and alpha 4. So these scalars are 1, negative 2, 3, and 2. When you look at this, this is actually a vector in R to power 4. In our next question, we need to find the coordinate vector for the polynomial p of x. So this p should be a small p. This should be p of x, a small p, because this is a vector which is picked from this space here. So we need to find the coordinate vector for the polynomial p of x, which is given in the form that is alpha naught plus alpha 1 of x plus up to alpha n x to power n. That is relative to the standard basis. That is relative to the standard basis for the polynomial space p of n. So to look at this, the most important thing is to first of all know what is the standard basis for the p of n space. So we are given p of x to be equaling to this, which means it is obtained from the p of n space, and p of n space means is having the dimension of n, is having the dimension of n, and for that case the basis must consist of n elements. So our basis is b, which is having elements 1, x, x squared, of course the next one will be x cubed, and the next one will be up to x to power n. So this is our standard basis. So when you are talking about a polynomial of degree 3, it means the standard basis will be 1, x and x squared, then x cubed. That is for the polynomial that is p of 3 space. P of 3 space. So that is a polynomial of degree up to 3. So its standard basis will be this. Then if we talk about p of 2, that is degree 2, so it should be containing elements that is 1, x and x squared. That will be p of 2 space. That is the standard basis. So this is the standard basis for p n of x. So if that is the case, then we need to obtain the coordinate vector, we need to obtain the coordinate vector. We need to obtain the coordinate vector. In other words, we need to obtain this vector here of P, the coordinate vector of P, which P, we are having it here, of this P relative to this basis. So we need to obtain this coordinate vector. So in order to do that, then we must write this P as a linear combination of the vectors in this basis. So we need to write this P. We write P as a linear combination, of the vectors, in the basis B, of the vectors in the basis B. So if we do that, it means our P will be of this nature, but we need also other constants such that we can write this P as a linear combination of these vectors here. So we can, if here we are using alpha naught, alpha 1, then we seek other scalars now. So we need other scalars. So we shall seek for other scalars, beta 1, beta 2, up to beta n, such that we can write alpha naught plus alpha 1 of x plus alpha 2 of x squared plus up to the last term, which is alpha n x to power n, must be equal to, we need to write this P as a linear combination of the vectors in this basis, that is 1x up to x to power n. This should be beta 2, so we should write this up to beta n, and beta n should be beta n then multiplied with x to power n. So that is what we should be having there. So for that case, you need to look for the values of what? For the values of beta naught, beta 1, beta 2, up to beta n. These are our scalars. So for the values, when you look at this one to be equal to this, it means you need to equate the corresponding components for x to power 0. For x to power 0, it means beta naught will be equal to alpha naught. When you talk about for x to power 1, it means beta 1 must be equal to alpha 1. So when you talk about for the coefficients of x to power 2, then beta 2 should be equal to alpha 2. This should be equal to this one here. So the trend will continue up to when you reach at beta n equaling to alpha n. So you are looking for these scalars here. You are looking for these scalars for which you can write this polynomial here as a linear combination of these vectors in the standard basis. So clearly we have obtained our scalars beta naught, beta 1, beta 2, up to beta n. So it implies our P, the coordinate vector of P relative to the standard basis B will be of the form our scalars were beta naught, beta 1, beta 2, up to beta n. So it means this will be of the form beta naught, of the form of the scalars that we have used, beta naught, beta 1, beta 2, and that will continue up to beta n. So this will be the coordinate vector of P relative to the standard basis B. So for that case, what is beta 1, what is beta 2, what is beta 3, and beta n? So beta naught is actually alpha naught. This is actually alpha 1. This is alpha 2. And this continues up to alpha n. So this will be the coordinate vector of P relative to the basis B. So this is what we shall obtain. we have so far seen about 3 to 4 examples. Let us look at this last example, then others you will be able to try them out. So we are given V, which is a vector space of polynomials that have got the degree which is less or equal to 2. So this is the V. V is having polynomials of the form at squared plus bt plus c, for which a, b, c are elements from the set of real numbers. You are given the polynomials e1, which is 1, e2, which is t minus 1, e3, which is t minus 1 squared, but which can be written as t squared minus 2t plus 1. These polynomials e1, e2, and e3 form a basis for V. Now, we are letting V, if you pick a vector V from our vector space V, such that your V is 2t squared minus 5t plus 6, we need to find the coordinate vector of V relative to the basis E, which basis E is having vectors E1, E2, and E3. As we said, we need the coordinate vector of V relative to this basis, and for that case, you must set V as a linear combination of the vectors in the basis. So for that, we shall have V equaling to, if our scalars is x, y, and z, then it means this will be x e1 plus y e2 plus z e3. That is what we shall have. So you already have your V, you already have your E1, you have E2, and you have E3. So you simply substitute for E1, E2, E3, and this V. Then after substituting, get the corresponding components for t squared, t, and the constant term on both sides. So after you have equated, you will be in position to get your x, y, and z. So having equated V to x e1 plus y e2, which is t minus 1, plus z e3, which is t squared minus 2t plus 1. So try to simplify this expression, equate the corresponding terms for t squared, for t, and the constant term. Then you should be able to verify whether you will be able to get your scalars or your constant values for x, y, and z to be 3, -1, and 2. After getting x as 3, y as -1, and z as 2, then you should be able to write your V now as a linear combination of E1, E2, and E3. So it means your V will be 3E1 minus E2 plus 2E3 using these values that you have obtained. But we are interested in the coordinate vector V relative to our basis, which is E. And as we said, you take the what? You take the scalars. You take these scalars that are helping you to make the linear combination. So your scalars are 3, -1, and 2. So this will be what we call the coordinate vector of V relative to the basis. And as we said, in case they give you the coordinate vector like this one here, and they ask you to get V, which is 2, -5, and 6, then you should as well be in position to obtain that. We are having question number 5, where we are having problems 1 to 2. So we are having part 1 and part 2, where basically you need to be referring to the matrix A, and your matrix A is having entries 2, 3, 4, and -7 in the vector space V of real 2 by 2 matrices. So you need to find the coordinate vector of A relative to the basis B of the matrix A. This one here, the coordinate vector of A, we are referring to this A. Then the basis, we are using the basis consisting of these matrices here. So you are interested in getting the coordinate vector of A relative to B. That is A relative to this matrix here. And for that case, express A as a linear combination of these matrices, get the values of the scalars, and get what we call the coordinate vector. So the next part 2, you are referring to the same matrix A, but for this case you are looking at a different basis. So you are looking at the basis actually, which is the standard basis, because you have 1 0 0 0 1 0 0. So this is the standard basis of a 2 by 2 space. So you want to get the coordinate vector of A relative to the standard basis. So this is the standard basis of a 2 by 2 matrices. So you should be able to obtain the coordinate vector of A relative to E. You will as well try out question number 6, where you need to find the coordinate vector of V, which V is given as -8, -5, and 0. That is relative to the basis S. Your basis is S, which is having vectors V1, which is 3, 1, -4, V2, which is 2, 5, and 6, and V3, which is 1, 4, and 8. So you should be in position to obtain this coordinate